Hi guys, so welcome back to my channel. Today, once again, we're going to discuss University Physics with Modern Physics, Volume 1, 14th edition, a book by U.D. Young and Roger A. Friedman. Previously, I discussed with you Chapter 12, which is about fluid mechanics. So today, we're at Chapter 17, Temperature and Heat. I'm also going to discuss 3 exercises and practice problems tutorial. I'm going to walk through 3 problems and we're going to solve them together step by step. So let's proceed with the first problem. The pressure of a gas at the triple point of water is 1.35 atm. If its volume remains unchanged, what will its pressure be at the temperature at which carbon dioxide solidifies or CO2 solidifies? So for this problem, since we know that temperature is directly proportional to pressure, we may use this formula, which is the first temperature divided by the initial temperature divided by the final temperature is equals to the initial pressure divided by the final pressure. Since they are directly proportional with one another. So let's list down the given. So for the initial temperature, we have 273 Kelvin because at the triple point of water, its temperature will be 273 Kelvin or 0 degrees Celsius, which is absolute zero. And for the initial pressure, we have 1.35 atm or atmospheric pressure. And for the final temperature, the temperature at which carbon dioxide solidifies is 195 Kelvin. So how do we know this? You guys can actually look it up in the internet. So it's a standard temperature or it's the default mode at which carbon dioxide solidifies. So we're looking for the final pressure since the problem asks what will its pressure be at the temperature at which carbon dioxide solidifies. So using the formula, we're looking for P2 or the final pressure. So with a little bit of algebra, we would isolate P2 at the left-hand side of the equation. So the final pressure is equals to the final temperature multiplied by the initial pressure divided by the initial temperature. So plugging the values that we listed down in the previous slide. So for the final temperature, it would be 195 Kelvin multiplied by the initial pressure, which is 1.35 atmospheric pressure, divided by the initial temperature, which is 273 Kelvin. And so plugging those values into the calculator, we would get 0.964 atmospheric pressure. So the pressure at the temperature at which carbon dioxide solidifies would be 0.964 atm. So that's it for our first problem. And for our second problem, the Humber Bridge in England has the world's longest single span, 1,410 meters. Calculate the change in length of the steel deck of the span when the temperature increases from -6.0 degrees Celsius to 17.5 degrees Celsius. So for this problem, since it's asking for the change in length of the steel deck of the bridge in England, we would use this formula, which is change in length is equals to the initial length times alpha times the change in temperature. So let's list down the given. So first, you can actually look in the table that the steel deck has a alpha value of 1.2 times 10 raised to -5 degrees Celsius raised to -1. So that's in the table, or just look it up in the internet and you will find that value. And for the initial length, so it's given in the problem, which is 1,410 meters. And for the change in temperature, it's -60 degrees Celsius to 17.5 degrees Celsius. So change in temperature means final temperature minus initial temperature. So we would get 23.5 degrees Celsius. So we don't need to convert it into Kelvin since Celsius and Kelvin have the same difference when it comes to temperature difference. So we don't need to convert it into Celsius anymore, or into Kelvin anymore. So we're looking for the change in length. So we just plug in the values that we got from the previous slide. So we have the initial length, which is 1,410 meters multiplied by the alpha, which is 1.2 times 10 raised to negative 5 degrees Celsius raised to negative 1, multiplied by the change in temperature, which is 23.5 degrees Celsius. So, calculating those values, we would get positive 0.40 meters. So, the change in length would be positive. So, it means the steel deck expanded because the change in length resulted to a positive value. So, for our last problem, problem number 3, you are given a sample of metal and asked to determine its specific heat. You weigh the sample and find that its weight is 29.7 newtons. You carefully add 1.50 times 10 raised to 4 joules of heat energy to the sample and find that its temperature rises 15 degrees Celsius. What is the sample's specific heat? So, since you're given the weight or the force, normal force, and you're also given the heat energy transferred, which is 1.50 times 10 raised to 4 joules, and you also have the change in temperature, which would be 15 degrees Celsius. So with those given values in the problem, we would use the formula for heat energy exchange or heat energy transferred. So Q is equals to the mass times the specific heat multiplied by the change in temperature. So that's for the formula, and we know that the mass or the formula for the mass is weight divided by gravity or acceleration of gravity. So we list that down and we list down the given in the problem. So the change in temperature is 15 degrees Celsius. Again, we don't need to convert that into Kelvin anymore since the Kelvin and Celsius have the same scale when it comes to temperature change. So let's just put it as it is. So for our heat energy transferred, it would be 1.50 times 10 raised to 4 joules as given in the problem. And for the weight or the normal force, it would be 29.7 newtons, which would be the weight. So the formula for mass would be weight over gravity or weight divided by gravity. So the weight is given in the problem, which is 29.7 newtons divided by the acceleration of gravity, which is 9.8 meters per second squared. So we have that. So let's leave those values in there. So going back to the formula or to our main formula, Q is equals to MC change in temperature. So we're looking for the specific heat of the sample. So we have to isolate C since it's the specific heat in the formula. So doing basic algebra, we would get C is equals to Q divided by mass times change in temperature. Since the formula for mass is weight divided by gravity, we would get, so the mass would become weight divided by gravity in the formula. So we have to flip that so we wouldn't have a hard time in computing for a fractional formula or fractional equation. So you would get gravity times Q divided by weight times the change in temperature. So far we all have the values that we needed that we can plug in into the equation. So we would get the gravity, which is 9.8 meters per second squared, multiplied by the heat energy transferred, which is 1.50 times 10 raised to 4 joules, divided by the weight, which is given in the problem. Again, the value is 29.7 newtons, multiplied by the change in temperature, 15.0 degrees Celsius. So reminder, we don't need to convert it into Kelvin since Kelvin and Celsius both have the same scale when it comes to change in temperature. So we would get 329.96, or if you guys want to round it off, it would be 330 joules per kilogram times Kelvin. So that's the unit of the specific heat. So thank you guys for taking the time to watch this video. I hope that you learned about temperature and heat. So thank you so much.